13.3, the fundamental theorem of line integrals, video 8. Let's take a look at another example of answering the question, are you a conservative vector field? And if so, we're going to find its potential. In the previous video, I didn't follow it with if so, find its potential, but it wasn't, so we couldn't have even if we wanted to. Speaking of finding your potential, I'm not sure if any of you are concurrently enrolled at UT Tyler or plan to attend UT Tyler in the future, but if you do, and if you're ever in the engineering building and you're going up the stairs to the top floor where most of the math classes are, you'll see a giant poster promoting the math department with the phrase, find your potential. Look closely at the math in the background and nerd out briefly, because it's a math joke. But I digress. To answer the question if this is conservative, we can take advantage of Theorem 6, which said if all these things happen, then the function is conservative. Well, we're not given a domain, but in the absence of a stated domain, you can assume that your domain is the largest set that makes these defined and real. Defined meaning don't let it be undefined, meaning no denominators equal to 0 or no logarithms of negative numbers. Or for tangent, cotangent, secant, and cosecant don't equal the things that make them undefined. And by saying the largest set that makes this both defined and real, avoid things that make it complex. So if we have square roots, we want to make sure that nothing gets negative. But these are polynomials. They're always going to be defined. They're always going to be real. So in the absence of a stated domain, you always assume the largest possible domain, which in this case would be R2. I can plug in any ordered pair I want. Well, R2 is an open and simply connected set, so we're okay there. And the derivatives, these are polynomials, so their derivatives and their antiderivatives will be continuous everywhere we want them to be, so no problem there. We just got to check the equivalence, the equality of the correct partial derivatives. So our I component function is 3 plus 2xy. Our j component function is x squared minus 3y squared. So capital P is equal to 3 plus 2xy, and capital Q is equal to x squared minus 3y squared. And we simply have to check the partial derivative of P with respect to y, and the partial derivative of Q with respect to x. The partial derivative of 3 plus 2xy with respect to y. This is 0. 2x is a constant with respect to y. The derivative of y is 1. So the partial is 2x. For the q function, the negative 3y squared is a constant relative to x, so its derivative is 0. The derivative of x squared is 2x. These are equal. Therefore, f is conservative. Great. So if I'm doing a line integral, I can evaluate it easily if I know what its potential function is. In other words, there exists some f, and if you're wondering what this backwards capital E is, go back a couple of videos. There exists an f such that, same thing for this symbol, go back a couple of videos. The gradient of lowercase f is equal to the vector function capital F. And if we're evaluating a line integral, we need to know what this lowercase f is, if we're going to take advantage of the fundamental theorem of line integrals. So how do we find that lowercase f, the potential? To find f of xy, we just have to now take advantage of the fact that this is the partial of f with respect to x, or p is the partial of f with respect to x, and q is the partial of f with respect to y. So we know that the partial of f with respect to x was 3 plus 2xy, and we know that the partial of f with respect to y was x squared minus 3y squared, because it was a conservative vector field. It was the gradient of something. So how do we recover the function? We just do some integration cautiously. I would start with one of them. I usually start with the partial with respect to x. And if you integrate that with respect to x, so integrated dx, Well, the fundamental theorem of calculus basically says that the integral of the partial with respect to x dx is the original function. The integral of the derivative is the original function. Over here, this is just an integral with respect to x. The integral of 3 with respect to x is 3x. The integral of 2xy with respect to x. The y is like a constant. The integral of 2x is x squared. So we get x squared y. And here's where you have to be careful. Normally when you do an indefinite integral, you put plus c. But this was the partial with respect to x, which means that if there was anything that contained only y's, it would have disappeared when we took the partial derivative. So the thing that might have disappeared that we're trying to recover isn't just a constant. It can be anything that has only y's. In other words, it could be some function of y. Because if we took the partial derivative of this with respect to x, this whole function would disappear. It has no x's. So now we have to figure out what that would equal. Again, when you integrate a function that was differentiated partially with respect to x, you don't pick up a plus c, you pick up an entire function of the other variable y. So how do we figure out what that is? Well, now we connect it to the other thing we knew about the partial derivatives. This implies that the partial derivative of the function f with respect to y, let's just differentiate this thing with respect to y. Partial derivative of 3x with respect to y is 0. The partial derivative of x squared y with respect to y is x squared. But the partial derivative of this function is just the same as the ordinary derivative, y. This contains only y's and no x's. So its partial derivative is just its ordinary derivative. So we can just put plus g prime of y. So how does that help us? Well, now we know two things about the partial derivative of f with respect to y. It's equal to this and it's equal to this. Well, the only way that can happen is if those things are equal to each other. So collectively, these two things imply that x squared minus 3y squared is equal to x squared plus the derivative of g of y. And now we can solve for this derivative for g of y. The x squareds cancel. They should, because this should only be a function of y. So negative 3y squared equals g prime of y. So how do we recover g? Well, how do you undo a derivative? Integrate. Let's integrate this with respect to y. And integrate this with respect to y. Fundamental theorem of calculus, integral undoes the derivative, so we have g of y. Over here we just have the integral of negative 3y squared, which is negative y cubed. And because this was only a function of y, there are no x's here, we do pick up a constant. But that doesn't answer the question. It doesn't answer what f equals, it only answers what this missing g of y equals. So if you put it all together, and I know I'm all over the place here, therefore, our potential function was, and this should go in a box because it's kind of important, 3x plus x squared y plus g of y, which is equal to this. So minus y cubed plus some constant. So you just have to chase it around. It looks like you're going in circles, but you're just connecting all the information you know to find what you don't know. Partial with respect to x is equal to that. Integrate with respect to x. Where we do, we don't pick up a constant, we pick up a whole function of y. Now hit it with partial with respect to y, equate these, isolate the derivative of the g function, integrate to recover the g function, now you pick up just a constant, and then build your potential. It's a lot of work to go through, but if we're evaluating a line integral of this, and we know that it's the gradient of this, now it suddenly becomes easy to evaluate the line integral, because we would just have to evaluate this at the end point of the curve, this at the initial point of the curve, and subtract the two results.